Let's continue with our study of representing functions as power series. So first, recall that the sum from n equals 0 to infinity of a r to the n is a over 1 minus r, and this converges as long as the absolute value of r is less than 1. So we need to make our 1 over 4 minus x into the form 1 minus some number. So how we'll do that is we'll factor out a 4 in the denominator. So that will give us 1 over 4 times 1 minus x over 4. And that's the same thing as 1/4 divided by 1 minus x over 4. So that means that in that formula we have that the a is equal to 1/4 and the r is equal to x over 4. So this is equal to the series summed from n equals 0 to infinity, a 1/4 multiplied by r to the n, x over 4 to the n, which you could express as a sum from n equals 0 to infinity, x to the n over 4 to the n plus 1. Now, this series will converge so long as the absolute value of r is less than 1. So the absolute value of x over 4 must be less than 1. Absolute value of x is less than 4, or x is in between -4 and 4. And because these are all based on geometric series, the geometric series will never converge at the endpoints. You don't need to actually test them. So the power series representation is given in blue, and its interval of convergence is -4 to 4. I'm just going to start by writing that the sum from n equals 0 to infinity, a r to the n is a over 1 minus r. Okay, so first of all, let's factor out a 2 in the denominator. We'll have 2 over 2 times 3 over 2 plus x. And those 2's can actually cancel, giving us 1 over 3 halves plus x. Now to apply that formula, this 3 halves has to be a 1. So if I factor that out, I'll have 3 halves times 1 plus 2/3 x. And 1 over 3 halves is the same thing as 2/3. My numerator, 1 minus -2/3 x. And so now I can apply this formula with a equaling 2/3 and r equaling -2/3 x. So the sum will equal a sum from n equals 0 to infinity, 2/3 multiplied by -2/3 x to the n power, which is the same thing as the sum from n equals 0 to infinity, let's say -1 to the n, 2/3 will be to the n plus first, and x to the n. And in this case, the radius of convergence, we need -2/3 x, absolute value to be less than 1. So the absolute value of x must be less than 3 over 2, and x must be between -3 over 2 and +3 over 2. So there is your interval of convergence. Next, let's find some power series that are not centered at 0. So in this case, we have to be centered at 3. And once again, just recall that the geometric formula is a sum from 0 to infinity. A r to the n is a over 1 minus r. So being centered at -3 means we have to have x plus 3 being our r. So if I make that 4 over minus the quantity x plus 3. See, I've actually added a negative 3 in the numerator, so to compensate I must also add a positive 3, so that I've added nothing effectively. So that becomes 4 over 8 minus x over 3. We need that 8 to be a 1, so factor out an 8. So 4 over 8 times the quantity 1 minus x minus 3 over 8, which is the same thing as 1/2 divided by 1 minus x minus 3 over 8. And now we can use the geometric sum formula with a equal to 1/2 and r equal to x minus 3 over 8. So this will be equal to the sum from n equals 0 to infinity 1/2 multiplied by x minus 3 over 8 to the nth. And there are other ways to write that, but I think that's good enough. And in this case, to find the interval of convergence, the absolute value of x minus 3 over 8 has to be less than 1, or x minus 3 absolute valued must be less than 8. X minus 3 we're between negative 8 and positive 8. And adding 3, we have that x is in between negative 5 and 11. And there's your interval of convergence. Alright, this one has some tricky algebra, or mostly tricky arithmetic actually. So centered at c equals 3. So we need to have a factor with x minus 3. So first we'll have 2, take out that 3, x minus 3. Now think, what you've actually added in is negative 9. We have 3x still and we have a negative 9, so to compensate we have to add a regular old positive 9. And that gives us 4 over 11 plus 3 times x minus 3. Now I factor out that 11, so that becomes a 1, and I'll have 4 over 11 times 1 plus 3 x minus 3 over 11. Eek. That's the same thing as 4 over 11 divided by 1 minus negative 3 x minus 3 over 11. Egats. Okay, so remember that we have the sum from n equals 0 to infinity. A r to the n is a over 1 minus r. So in this case my a is 4/11. So I have a sum from n equals 0 to infinity, 4 over 11. The r is negative 3 x minus 3 over 11. So negative 3 x minus 3 over 11, all to the power of n. And just simplifying that slightly, not that it looks much simpler, we'll have negative 1 to the n, 4, that 4 isn't raised to any power, just that constant, 3 to the n, and then x minus 3 to the n, and the denominator will have 11 to the n plus first. Okay, now let's find our radius of convergence. So this will converge if the absolute value of r, which was negative 3 x minus 3 over 11, is less than 1, which tells you that 3 x minus 3 absolute valued must be less than 11. So negative 11 is less than 9x minus 9, which is less than 11. So adding 9, we have negative 2 is less than 9x. Oops, that should have been 3x. So 3x minus 9, 3x, which is less than 20, in which case the interval of convergence is negative 2/3 to 20/3. Find a power series for this function g of x centered at c equals 0. So because we don't have a linear factor in the bottom, my idea is that we could try partial fractions. So 4x over x squared plus 2x minus 3 that would be a over x minus 1 plus b over x plus 3. And that gives us 4x equals a times x plus 3 plus b times x minus 1, or 4x equals x times a plus b, and then plus 3a minus b. And because we have 4x, we know that 4 has to equal a plus b, and because we have no constants on the left side, 3a minus b must equal 0. And that implies that 3a must equal b. So that using that, we have 4 is equal to a plus 3a. 4 equals 4a, and therefore a is 1. And if a is 1, going back to here, we figure out that b has to be 3. So that tells us that g of x is equal to 1 over x minus 1 plus 3 over x plus 3. Now 1 over x minus 1 is the same thing as negative 1 over 1 minus x. You can get that by multiplying or dividing both the numerator and denominator by negative 1. The second fraction we'll make into 3 over 3 times 1 plus x over 3. So we have negative 1 over 1 minus x plus 1 over 1 minus negative x over 3. So now this first series will sum to be a sum from n equals 0 to infinity. Negative 1 is my a. I'll just have x to the n. The second one, sum 0 to infinity. 1 is my a, and we'll have negative x over 3 to the n. So that's the same thing as the sum from n equals 0 to infinity. Negative 1 plus negative 1/3 to the n, all multiplied by x to the n. The next thing we need to do is to find the interval of convergence. So the first series that we had was the sum from n equals 0 to infinity, negative 1 x to the n. And this converges if the absolute value of x is less than 1, which implies that we have an interval convergence from negative 1 to 1. Now the second series we had was a sum from 0 to infinity, negative x over 3 to the n. And this converges if the absolute value of x over 3 is less than 1, which implies that the absolute value of x is less than 3, or the interval of convergence for the second series is negative 3 to 3. So the second series has a larger interval of convergence, but the interval of convergence of the entire series is found by intersecting these two. So you have to have both series converge for your sum to converge. So since negative 1 to 1 is more restrictive, that will be the interval of convergence for our sum, negative 1 to 1. You can think about it as two intervals overlapping. You have negative 3 to 3, and then you have negative 1 to 1. Where they both are is where they intersect, so that's the part where the whole sum will converge. Alright, this one, so same kind of idea. So we have the sum from n equals 0 to infinity. A r to the n is a over 1 minus r. In this case, the a will be 2, so this will equal a sum from 0 to infinity. 2, r is x squared to the n. So that's the sum from n equals 0 to infinity of 2 times x to the 2n. And this will converge so long as the absolute value of x squared is less than 1, which implies that x is in between negative 1 and 1. So the interval of convergence for this particular series is negative 1 to 1. So this one is similar to the previous one, except for we have to do a little bit of manipulation first. So first factor out a 7 in the denominator. So I'll have 7 times 1 plus x squared over 7. And that's the same thing as 1 over 1 minus negative x squared over 7. So this will equal a sum from n equals 0 to infinity, 1 times negative x squared over 7 to the n, which is the same thing as the sum from n equals 0 to infinity. I'll say negative 1 to the n, x to the 2n, all over 7 to the n. Now we will have convergence so long as the absolute value of negative x squared over 7 is less than 1, which means that x squared must be less than 7, which means that x is in between root 7 and negative root 7. Or you could say that the interval of convergence is negative root 7 to 7, not including the endpoints. Now another technique to find a power series was to use different relationships between derivatives and integrals. So for ln of x plus 1, notice that the derivative of ln x plus 1 is equal to 1 over x plus 1. And we can find a power series for this. And so if I find a power series for 1 over x plus 1, then I can integrate it, and that will give me a power series for ln x plus 1. And the radius of convergence will be the same, but the interval may have changed slightly. So let's start by finding a power series for 1 over 1 plus x. Not very hard, that's 1 over 1 minus negative x. So we have the sum from n equals 0 to infinity, negative x to the n, which is the same thing as the sum from n equals 0 to infinity, negative 1 x to the n. And so ln of x plus 1 will equal, a series for that will equal the integral of this series. And that will be the sum from n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. Next, let's find the interval of convergence for this series. So we know that the original series had interval of convergence negative 1 to 1. So the only thing we have to do here is test the endpoints. So if we test x equals negative 1, that gives us the sum from n equals 0 to infinity, negative 1 to the n, negative 1 to the n plus 1, all over n plus 1. Now, this particular series is the same thing as the sum from n equals 0 to infinity, just negative 1 over n plus 1. You can verify that by just starting to input some numbers. Like say you input 0, the negative 1 to the 0 is 1, negative 1 to the 0 plus 1, or first will be negative 1. When you input 1, the first one's negative, second one's positive. When you input 2, it's flip-flops. But anyway, one of those two will always be negative. And this series diverges, so we do not have convergence at negative 1, but at x equals 1, we get the series, so a sum from 0 to infinity, just negative 1 to the n, 1 to the n plus 1 is just 1, over n plus 1, and that would converge by the alternating series test. So for ln of x plus 1, my interval of convergence does not include negative 1, but does include 1. We'll use a similar relationship to find a power series for arctangent of 2x. So notice that f prime of x is equal to 2 over 1 plus 2x squared. That 2 in the numerator came from the chain rule, which is the same thing as 2 over 1 plus 4x squared. And I can find a power series for this expression, and then if I integrate it, I will get an expression for arctan. Okay, So let's find a power series for 2 over 1 plus 4x squared. That's the same thing as 2 over 1 minus negative 4x squared. So this is equal to a sum from n equals 0 to infinity, 2 multiplied by negative 4x squared to the n, which is the same thing as a sum from n equals 0 to infinity, 2 negative 1 to the n, 4 to the n, and x to the 2n. So now to find the series for arctan of 2x, we have to integrate this. So you have the integral of the sum from n equals 0 to infinity, 2 negative 1 to the n, 4 to the n, x to the 2n. And that will be the sum from n equals 0 to infinity, 2 times negative 1 to the n, 4 to the n, x to the power of 2n plus 1, divided by 2n plus 1. Now our original series, the one we had before integration, this would converge so long as the absolute value of negative 4x squared is less than 1, which means x squared must be less than a quarter, or x is less than a half but bigger than negative 1/2. So what we need to do then is test positive 1/2 and test negative 1/2 and see what happens. Alright, first let's test x equals negative 1/2. So when we plug in negative 1/2 for x, we have a sum from 0 to infinity, 2 negative 1 to the n, 4 to the n, negative 1/2 to the 2n plus 1, all over 2n plus 1. So that's the sum, n equals 0 to infinity. Now, one slightly tricky thing is that 2 times 4 to the n, so first of all, 4 to the n is the same thing as 2 to the 2n. And so 2 times 4 to the n is actually 2 to the 2n plus 1. And then we have this negative 1 to the 2n plus 1, and then a 1 over 2 to the 2n plus 1, all divided by this 2n plus 1. But the point being is that this 2n plus 1 will cancel that 2n plus 1, giving us a sum from n equals 0 to infinity, negative 1 to the n, negative 1 to the 2n plus 1, all over 2n plus 1. And if this series truly alternates, then we are going to have something convergent. But if it doesn't alternate, it won't. So let's just test some things. If we say plug in 0, negative 1 to the 0 is 1, negative 1 to the 1 would be negative 1. So the first term is negative. If we plug in 1, negative 1 to the first is negative. So we had the first term was negative. I think the second term is positive. Appears to be, right? So first plugging in 0, positive, negative. Second term plugging in 1, negative, and negative making a positive. Plugging in 2, positive, negative, making a negative. Yep, this is going to alternate. So this will converge by the alternating series test. And at x equals 1/2, a similar cancellation will happen. It's just the case that there'll be no extra negative, so we get the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1, which also converges by the AST. So for this particular example, my interval of convergence is negative 1/2 to 1/2 inclusive. Next, let's use differentiation. So we have that the function f of x that we care about, we're told that it's the second derivative of 1 over x plus 1. So if we find a power series for 1 over x plus 1 and differentiate it twice, we'll have a series for f of x. So first of all, 1 over 1 plus x, same thing as 1 over 1 minus negative x, which is a sum from n equals 0 to infinity, negative 1 to the n, x to the n. So if we differentiate that once, so we'll say the first derivative of this is equal to a sum from n equals 1, because the first term gets lobbed off, negative 1 to the n, x to the n minus 1. And f is equal to the second derivative. So if we take one more derivative, we'll have a sum now from n equals 2 to infinity, negative 1 to the n times n minus 1, x to the n minus 2. So that's perfectly good enough. Now, just in case it happens, it might be the case that the indices can get changed. So if I say made this start at 0, negative 1 to the n is still fine. It still is positive and negative in the right order, as in the first one's positive, the second one's negative. That n would become an n plus 2, then an n plus 1, and then an x to the n power. So it's an equivalent expression of that series. You don't have to do that, it's just good to know that it's possible. Now, the original series had an interval of convergence negative 1 to 1. We just need to test our endpoints, but pretty sure in both cases this fails the test for divergence, so this thing also has an interval of convergence negative 1 to 1. Because the limit of the terms is not 0 in either case. One application of these infinite series is to use them to approximate values of functions at non-trivial x's. And this is actually how many calculators get, say, decimal expressions for sine, cosine, natural log, e to the x, and stuff like that. It's actually, if you look at your calculator and how it does it, it'll say, I use a Taylor polynomial of degree blah, centered at blah, to do this problem. So we'll learn specifically how to find these, but this is called the fourth degree Taylor polynomial approximation of ln x, and it is centered at 1. We're going to use it to approximate ln of 1.1. So ln of 1.1 is about equal to inputting 1.1 into every spot. When you do that, and even though it's really tedious, the operations are just arithmetic, so if you had to do them by hand, you could theoretically do that. This is equal to 0.0953083, and you get that by inputting 1.1 for every single x. Since this approximation is centered at 1, as you can see all the x minus 1 terms, it is most accurate for numbers near 1. You wouldn't want to find ln of 502 using this expression. You want to use something different. And now the next thing we can do is determine an upper bound on the error. And so we learned in a previous section, because this is an alternating series, we learned that the remainder of using the first 4 terms is less than or equal to the absolute value of the next term left off. And the next term left off would have been 1/5 x minus 1 to the 5th, so 1.1 minus 1 to the 5th, which is equal to 0.0000, so 5 zeros, and a 2. So really that's quite accurate. So if your calculator is only giving you 3 places of accuracy, I mean, you wouldn't notice the difference between this and, say, a polynomial of 5th or 6th degree. So use the series for arctan x to approximate arctan of 0.5 using the remainder of less than 0.001. So we want to have accuracy of less than 1/1000th. So the derivative of arctan is 1 over 1 plus x squared. The first thing we have to do here is get a formula for arctangents series. So 1 over 1 plus x squared is the same thing as 1 over 1 minus negative x squared, which is the same thing as the sum, 0 to infinity, negative x squared to the n, which is the same thing as 0 to infinity, negative 1 to the n, x to the 2n. So that is a series power series for 1 over 1 plus x squared. Now we want to find one for arctan, so we'll have to integrate this. So arctan will equal the integral of this, so that'll be a sum from n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. Now we need to find an n such that the remainder is less than 0.001. So we need r sub n to be less than or equal to 0.001. Now we know that r sub n is less than or equal to the absolute value of the n plus first term, and that n plus first term is x to the 2 times n plus 1 all over 2 times n plus 1, or x to the 2n plus 3 over 2n plus 3. And now at this point in time, what you do, using your x value you care about, we care about 0.5, you plug in x equals 0.5, and you test various values of n, say n equals 1, n equals 2, n equals 3, until you find one where this expression is less than 0.001. And the first n where that happens is n equals 3. So we are going to use the first 3, well, up to n equals 3, it's actually the first 4, because you start at 0. So 0, 1, 2, and 3. So arctan of 0.5 will be about equal to a sum from n equals 0 to 3, negative 1 to the n, 0.5 to the 2n plus 1 over 2n plus 1. So plugging everything in, first when we plug in 0, we actually just have 0.5. When we input 1, we have minus 0.5 to the third over 3. Inputting 2, we'll have plus 0.5 to the fifth over 5. And then inputting 3, we'll have minus 0.5 to the 6/7 over 7. And that's about equal to 0.463467262. And you know that the error is guaranteed to be less than 0.001. So there's your approximation.